This begins E569 discussion on Tuesday, October 22nd, 2013.
Hi. Uh, let's begin the discussion. So today I'm going to talk about C++ libraries which are good for matrices. I'll also introduce principal component analysis. Finally, there is a note on k-means and some hints for homework, and I'll talk about some sample problems. So a lot of students have asked questions where like they don't want to keep going between MATLAB and C by taking the matrix inverse in MATLAB. So we are allowing the use of template libraries. For linear algebra, some of the very common libraries are CBLAS and LAPACK. However, most of these are Fortran libraries. So CBLAS is the conversion of Fortran library BLAS, whereas LPACK++ is conversion of LPACK, which is again in Fortran. Armadillo and Eigen are for C++, but they use CBLAS or another variation of these original libraries which are Fortran based. So you can use these. We would not prohibit you from using these. These are usually used for very high computation operations, like when matrices of high dimension data are used, which is not a requirement here necessarily. So and it is not easy to deal with the Fortran codes. So we would recommend that you use OpenCV instead. OpenCV library is pretty vast. Like if Armadillo is about like 10 MB, then OpenCV will be about 70, 80 MB. However, I don't think so that should be a concern for you guys. So I would recommend that you go with OpenCV. There are a lot of advantages to it. It is very popular in industry. It's an open library. So you can look at the source codes. You can modify them according to your needs. You don't have to worry about the licenses. And it has lots and lots of algorithms which we use, and you can directly use those algorithms. However, in this course, we'll prohibit you from using algorithms. We expect you to understand and code in your own way. So we'll allow the use of OpenCV. You can download it from this link. There's a lot of good documentation available online. So which functions are we allowing for this homework? A CV array, it's a data type in which you can create dense matrix. For sparse matrix, there is another function, but you don't need that. This class is good enough for your problem. You could also use CVMat, but CVMat is obsolete. Instead, you could use class mat, which is again in terms of definition, it uses CV array internally, but that's okay. And you can use SVD. Why would you need SVD? Is you would need it if you attempt the bonus question for PCA. And you can also use the corresponding operators. However, certain operators we would like you to avoid, like mat class has operator mult. it allows you to multiply two matrices and so on. So we would still want you to use for loops for everything else. We haven't made a decision as to whether to allow you to do all these things, because this will change everything in the MATLAB guidelines and have corresponding effect for MATLAB functions. So we have not reached a decision yet about that. So you cannot use those operations. So only the only places you can use these functions are for obtaining the matrix inversion in part 1, problem 1, and for k-means algorithm in problem 3, and PCA in problem 3. So you're not allowed to use any other functions like perspective transform. It does the same thing what you're going to do. You're going to do perspective transform as such in part problem 1, where you're transforming the image into various sizes, shapes. So you're not allowed to use perspective transform. You have to write your own code for that. All you can use is CV invert. These are the functions. These are the classes. Invert is good enough for regular square matrix inversion, and it is also good enough for pseudo matrix inversion. When a matrix is not square or a matrix is singular, you need a pseudo matrix. So by default, if it's an invertible matrix, it will return you the same matrix as pseudo inverse will return you the same matrix as the actual invert function should give you. Otherwise, it will return a pseudo inverse. What is pseudo inverse? Okay, it's a very simple concept from linear algebra, where a matrix is not invertible. Then you preserve the linearly independent columns and rows and get an approximate inversion, which projects whatever transform you want to do to the linear space, which is independent. I'll quickly give an example for OpenCV, how to initialize the matrices. You'll have to read the documentation. I cannot extensively provide enough information about how to go about using OpenCV. However, there is lots and lots of documentation, as I'm stressing again, online, so you can use that. Please don't use codes which are available directly. Write your own codes, and if you do use algorithms from online, please cite them. Plagiarism is a serious issue, okay? So mat is a class, so you can initialize. Suppose you're using second order warping function. So for that, how many variables are there? 7, right? So here I'm selecting a 7 by 9 matrix, assuming that you have 9 control points. How many minimum control points you should have? Second order? 6? Why? How many variables do you have? 6 variables, so 6. But is that necessarily a minimum? I can still have less number of control points, right? And obtain a pseudo inverse. So there is no theoretical bound, lower bound on how many points you select for a transformation, obviously more than one. But it is always advisable to at least go with the with the number of variables you have. So you should have at least a 6 by 6 matrix invertible. I don't know why I wrote 7 by 9. It should be 6 by 9. In any case, I'll change this before posting it. So assuming it's 6 by 9, so if you have to make this matrix, you just call the constructor. You can call the constructor in many ways. This is the simplest way, where you give in the input of number of rows, number of columns. This is what variable type you want to assign the matrix to. It could be unsigned char, it could be unsigned int, right? So this is how it's defined. This is a macro for a type defined already in CV. So if you want to, can I have the overhead camera, please? So suppose I want 8-bit unsigned, char, complex number. So how would you code it in CV? I can see it. Can I have the overhead camera on the projector? Great. So this is general format where n is the number of bits you want to assign to the data type. T is the type itself, like floating point, unsigned char, and so on. And C denotes whether it's complex or not. So in this case, I've written CV32F. This means it is 32-bit float, right? So this is how you can code any data type. You can look it up in the documentation. Can I have it back on the computer screen? Yeah. Scalar all 0. This will just return zeros. Now scalar all can return tuples of ones, twos, and so on, up to 4, I think. So since you're assigning, this is a 2D matrix and each is just one value, so I have written scalar all 0. However, if you were to use this as a pixel, as an image, then you can use, if this were an RGB image, then you could have scalar all 0, 0, 0. So what would this do? This would make each pixel or each location in the matrix assign 3 values to it. And each of that will be a 32-bit float, right? So this is how data structure coding can be done in OpenCV. It's very intuitive, actually. And what basically this does is this initializes with zeros. You can give some other value also, and you can drop this parameter completely. This is an optional one. Then once I've created, I've instancized the MATM, then I'll call a function to fetch the control points. This, I've left it for your imagination. How do you want to call it? Like, give the image size as input, and what kind of figure it is, shape it is, pentagon or square or circle. According to that, it'll just return control points. So once you have the control points, you compute the inverse like this. So MAT has several methods, which I was talking about earlier. So you can use INV, or you could use CV invert. In that, you'll have to, CV invert would not allow the use of MAT because CV invert is basically an obsolete function. It's of C, and MAT is for C++. But in any case, you can, if you use CV invert, then you have to define CV array, not a MAT class, okay? In any case, and then you have several options, several flags you can set, whether you want to calculate the inverse by LU decomposition, QR factorization, or SVD decomposition. So here I've used SVD decomposition. Internally, it uses SVD decomposition to estimate the pseudo inverse. As I mentioned before, you don't have to worry about whether this pseudo inverse will be useful in all cases, because by default, if your matrix is invertible, pseudo inverse will be equal to your inverse. There are other operations which you can do after this normal processing, and then finally you release the memory which you have. This is the destructor basically. So this is just an example. So by the in between, this is where you do all your operations. Now going to dimensionality reduction. First of all, why do we need to reduce the dimension of any features? Or here I'm calling the outputs of filters, specifically in problem 3. When you apply the filters, you obtain features which you're using to do some machine learning process to make some decisions, right? So those are called features. So that's what I'm using features here for. So why a high dimensional feature space is not a good idea? So if suppose I keep on increasing the dimensions of feature, right? Then what happens? I have limited number of data points, right? Because the limited data points are always data you collect from your own methods by extracting features, or it's available from various sources depending on what kind of problem you're solving. So here you're calculating the data features by yourself. So if I keep increasing the dimension of the features, my data point is limited, my data set is limited. So what happens is the space becomes large and large. However, the data points are limited. So there's a lot of sparsity in the space. So if I want to make any statistical decisions, all algorithms make some kind of statistical decision. So if I make some statistical decision, it will not be accurate because I don't have sufficient data points to make that information in that dimensionality. Secondly, lot of features or a lot of dimensions are correlated to each other. So they have a lot of redundant information, which is not useful. And processing high dimensional space is also computationally expensive. So there are two common methods of dimensionality reduction. One is feature selection and the other is feature reduction. So in feature selection, you don't do any kind of transformation or wrapping. You just select the features. So if you have 10,000 dimensional feature, then you just select a few of those. How you select them depends on the algorithm. What is your purpose in selection? You want to restrict or use only those features which provide the maximum information or which provide the maximum distinguishability between separate domains of information which you're trying to process. So here we're going to use feature reduction technique. Principal component analysis is very frequently used for dimensionality reduction. It's also known as Governor Love transform. It's scale transform. It's very common in DSP. Basically, it just transforms your basis to an orthogonal basis. So the motivation behind principal component analysis is, first of all, you transform the data in such a manner that the resultant basis is orthogonal to each other. That is the first requirement. Second, the direction of your basis is such that the variance is maximized between different features. Now, what do we achieve by making the variance maximum between different feature dimensions? And what do we achieve by making something orthogonal to each other? Recalling from linear algebra, again, orthogonality ensures what? Uncorrelatedness. So you make your features uncorrelated. Is this a good thing? Not always, but yes, most of the times. So this is just an example of how, if this is, suppose you have a three-dimensional data and it's spread out in the space like this. However, there is maximum variance in this plane. So when you do principal component analysis, it will project the data on this plane. You certainly lose information, right? Because you're going from 3-dimension to 2-dimension. However, this is sufficiently good enough to characterize the different regions. These regions are assumed to be of different classes. So what does principal component analysis does? It retains the significant information by transforming the original space from a high dimension to a lower dimension. So the covariance matrix of original, since you're talking about a high dimension space, the original covariance matrix, if suppose if you have suppose 10,000 data points and 1 million feature dimension, then you have a matrix of 10,000 by 1 million, right? What is the largest possible rank of this matrix? 10,000, right? So what does this mean? Beyond 10,000, there is a lot of dependency, right? That is what the rank of a matrix tells you. So if you reduce the dimension to at least 10,000 or even below, then it's significantly useful, right? So how does this reflect in terms of eigenvalues? Eigenvalues for when there is a lot of dependency in linear dependency in vectors, then the eigenvalues will be 0 or close to 0. So you can ignore those eigenvalues, and you can that's how you can reduce the dimensionality and make a transform. So now skipping the details of PCA where you develop the theory for it based on the requirements which I stated above, I'll quickly go to how much you're supposed to know for this part of the problem. So PCA can be obtained using SVD, singular value decomposition. It can also be done using eigenvalue decomposition, but eigenvalue decomposition limits you to only square matrices. So the most general form is using singular value decomposition, right? So if you have a feature matrix of size X, feature matrix X of size n by m, where n is the number of features and m is the number of data points, okay? Let xi denote the number of denote the ith column. So what is each column? Each column corresponds to one data point, right? So you have each column would be a n by 1 vector, right? So let this denote a vector. Then you compute the mean of the feature space. So for that you will take the sum of all the columns, right, and divide by the number of columns. And again here a mistake. This should be m. Anyway, I'll correct it later on, because this is the mean of all the features, so this should be m. Once you have computed the mean, subtract the mean from all the features. Basically, you're centering your data. You're centering the data by removing the mean, right? So subtract the mean from each of the columns, right? Let us call this matrix, which has all the features, zero mean features. Let us call this Zx. Perform SVD of Zx. SVD is given by this equation. SVD is equal to SU S V transpose, where U and V are unitary matrices. U is of size n by n, V is of size m by m, and S is a matrix which contains the eigenvalues or the singular values, and it is of size n by m. Okay, so for this you can use CV SVD, or you could use the SVD class and its methods to calculate SVD. Either is okay. For MATLAB, there is a function SVD, which you could directly use, and there is another function called SVDS, which calculates only the top 5 or 6. Like you can specify how many singular values you want to obtain. So for a matrix of size n by m, you will have n singular values, where n is less than m, right? But if I don't want to calculate all the n values, I just want to calculate 1 or 2 values, so I can use that function SVDS. You can do the similar thing, I think, in SVD class, but you cannot do the same thing in CV SVD. So now how is this related to dimensionality reduction? Now, as I mentioned before, the eigenvalues correspond to the directions where the variance is maximum among the data. So by throwing away or discarding the eigenvalues of singular values, which are very small, we can reduce the dimensionality of the data. So if now S is of size n by m, and it has n singular values along the diagonal, so I can throw away some of those singular values. Now for this, assume which ones should we retain? The largest ones, right? Because you have to throw away the small ones. So if I want to reduce the dimensionality from n to say n prime, where n prime is less than n, so I would retain only the first n prime largest singular values. Does that make sense? Okay, so once we have the matrix U from previous step, if I want to reduce the dimensionality by n prime, I would just retain only n columns from U. Okay? So U is n by n matrix, right? So I will just retain n prime columns. So finally UR be the reduced unitary matrix. So this will be of size n by n prime, right? Because I am retaining only n by n prime columns. Anyway, finally the transformation step. So in this step, you use the zero mean feature vector, and you use this reduced unitary matrix, and this is how you obtain the transformation. So this is your origin. This is your feature space. This is your original feature, and this is the reduced feature. Now, since you've reduced n to n prime, what will be the dimension of Rx? N prime by m, where m is the number of data points. So this would be useful in homework 3 bonus question. You can try several values of n prime because you have 25 dimensional features, so you can try several values and discuss it in the report. For k-means, Sanjay discussed the algorithm in detail last time, so I'll just point out some details. How do you select the initial clusters? You can use them randomly, initialize all of them to one value. Is that okay? No. Can you hard code? No. K-means was not discussed? The algorithm was not discussed? Oh, okay. So let me discuss the algorithm. Operator, can I have the overhead camera? Please may I have the overhead camera? Now suppose this is my feature vector. This is first data point, second data point, and so on. This is mth data point. So each is n by 1 vector, right? Now I have to cluster them into k clusters. Let's call these xi to x1 to xm. So this is like column 1. So basically I have to assign each xi a label, which will be 1, 2, 3, 4 to k. Okay? What does this label tell me? This label tells me that this feature vector xi belongs to category 1, 2, 3, 4, or 5, right? So if you're doing clustering, you will cluster these into k groups, right? So eventually what you have to basically do is you give this as input, you get a vector y, which is of size m by 1. If this is n by m, this will be m by 1, and each of the m locations will give you the labels or the category of the vector. Yeah. Yes, I'm going to that. I'm just building up the notations. So first you need a concept of distance between 2 points. To do k-means, you need a concept of distance between 2 points. There are several distance metrics you can use. One most common is right? You can use the Euclidean norm. What are the other distances? You can use Rayleigh norm. Gaussian norm, and several others. The k-means code which we have provided, I think it by default uses Euclidean norm. So, but OpenCV k-means and MATLAB k-means, they provide you other options if you want to try different distance matrices, distance metrics. So what does this define? This defines how you measure the distance between 2 points. Okay. So now let's assume this is a two-dimensional space. These are your data points. And you have to cluster them in 2 groups. So clearly you can say that these are close enough to each other and these are close enough to each other, right? So your k-means should assign label 1 to all these points and label 2 to all these points, right? So how do you go about labeling these points? You have to start somewhere, right? So let's say I calculate the mean of all these vectors, and mean is somewhere over here. Okay, then I calculate the standard deviation, right? So standard deviation is about this much distance, right? Then I can create 2 cluster centers, since I'm assuming k over equal to 2 here, okay, in this example. So what will I do? I'll take 2 centers, cluster centers, C1 and C2. These are cluster centers. So let me assign C1 as mean minus the standard deviation and mean plus the standard deviation. Okay? This is how I want to initialize my clusters. Now once I have the initial clusters, what do? I calculate distance of each point from C1 and C2. Okay? For xi, let distance between C1 and xi be greater than distance between C2 and xi. So if this is the case, then what label would be xi? What? 2. Why? Because it is more closer to, yes. No, I'm assuming that this is k equals to 2. If you have k equals to 5, you'll have different initialization method. You'll have 5 cluster centers, and everything will be exactly the same. Yeah, that's it. You have to assume a k because it doesn't know how many clusters you want. So for k means, you have to specify the k. So for in case of problem 3, I think for the part 3.1, you have 12 textures and you have to classify them into 4 groups, right? So you're looking for 4 clusters. So k will be equal to 4 for that problem. Similarly, for the next part, you have a composite texture image, I think, which has 6 different textures. So for that, k will be equal to 6 and so on, right? So this example is just when k is equal to 2. So now you have this distance and you assign xi equal to, label of xi equal to 2, right? So you do this for all I. That is all the data points between 1 to m. You have m data points, right? Now, is this good enough? Is this method good enough? So now, suppose this is my Suppose this was my initial cluster. It will assign these to label 1 and these to label 2. This one would probably have a confusion. It will be probably assigned to 1 or 2, I don't know. Let's assume it goes to 2. So can you improve this further? Can you improve the algorithm further? Now once you have the labels, break a tie. You can assign it to either one. Actually, it depends on how your algorithm works. You can set that option in MATLAB at least. I'm not sure about CV or OpenCV. There are break tie conditions which you can give. And there are several ways to initialize. Some algorithms accept the initial centroids, some don't. It's recommended that you set your own initial centroids, but you cannot hard code them. Anyway, so getting back to the problem, you have already computed the labels, right? Now, with the computed labels, you can again calculate the new centers, right? Once you have labels, you have two distinct clusters, right? So now you can calculate C1, 2. This shows second iteration, okay? So C1, 2 would be equal to sum of all xi's into, say, identity matrix, which is label equal to, label equal to Ci. So this will give you 1 when label is equal to 1, and this will give you 0 if label is equal to 2. Okay? Upon number of this. C2 of second iteration would be equal to summation overall M xi it's summation of all the labels. Basically what I'm doing is I'm taking mean of only those clusters. So I'm taking here, what does this do? I'll explain, just one moment. Let me write this down. So I of label equal to j is equal to 1 when label equal to j, it is 0 otherwise, right? So this is my function. So what does this do? Sorry, there'll be a denominator here also. So what does this calculate? You take the vector, you multiply it by 1 or 0. 1 if its label is 1, 0 if its label is 2, that means you're dropping that vector. Divide by the number of xi's in cluster 1. Similarly, number of xi's in cluster 2. So basically you're taking mean of this region and mean of this region, and you're assigning them as centroids. Is this logical? Right? Because you want to shift you'll start shifting your mean towards the center of the mass of your region. Then you again assign labels for all points. God, my handwriting is terrible. Yeah. You tell me. So you keep on going, right? Endlessly. When do you stop? One condition, when labels don't change anymore. This is difficult to check computationally. Not really difficult, but computationally, yes. So what is the other condition I can use? My centroid of nth iteration is very close to my centroid of n minus 1, right? Same goes for C2 and so on. So when my centroids stop shifting anymore, that means I have reached a consensus in assigning the labels to the cluster. Now, what are the problems you can run in with this algorithm? I know it's not really a part of this course, but since we're touching k-means, let's discuss this. And we might ask this in midterm. Anyway, so what are the problems you can run into with k-means? How do you initialize affects your final result, right? So if I initialize two very bad vectors, I'll reach a consensus, definitely, because every time you're trying to reduce the variance between the distance between the two clusters. So it will definitely converge to some problem. But is that solution optimal? So there are chances of running into suboptimal solutions, okay? And there are really no good methods to initialize, and there is no universal known way to deal with the problems. However, recommended things are you start again and again and do this operation like 10 times, 20 times, and make sure you're and then take centroids, something like bootstrap. Do you know what bootstrap is? Statistics? Anyway, so you do this process, entire process of converging to two clusters, say 5 times, and then you have C1, C2, first try, second try, fifth try, right? Then you check the consistencies of C1, C2, and select which is most consistent. And each time you initialize from a different location, right? Because if you initialize with the same location, you'll end up with the same centroids, right? Now, what if k is equal to 6, like in 3b? How do you initialize? For 2, it was easy, right? Take the mean, subtract the standard deviation, and initialize, right? For k equal to 6, any ideas? Do the same thing. Right? Then I get 2 clusters, right? I calculate the distance of each point from its centroid, and I take sum of all that. If there is a lot of variation in this, take absolute value of the distances, then I split this cluster into 2. If this is good enough, then I don't split it. I keep on splitting clusters. Yep. That means, yes, you have to decide a threshold. So the distance of all the points is very close to the centroid. So there's the variance, or you can calculate variance or standard deviation. You can use any statistical measure. So if it is less than certain threshold, then you say that, okay, this cluster is stable enough. I don't need to break it in 2 different clusters. This is one way. Randomly select 6 data points as cluster centers. You can do this also, right? You randomly select any 6 data points out of your m data points and call them as cluster centers and keep running the algorithm, right? Hopefully it will give you something reasonable. I think we are running out of time. Let's go back. Can I have the computer screen on the, yeah. Okay, so This is what I was talking about, splitting the clusters. Hard coding of cluster centers is not allowed. So you need to find out a way of defining the clusters. For C, again, I'll have to brush. Okay. Some of the very commonly asked questions for homework 1, homework 3, problem 1. Do we need to use first order or second order? You can do either. We don't care. But your result should be good. Which is another way of saying very nicely that do it with second order. Anyway. So does the pentagon have to be a regular pentagon? Again, we don't care. It should look like the image which has been shown. You can have a little gap below or above, but it should be very close to the example which is shown. How to get the corner points? It's really up to you, but a very simple method which Sanjay has been telling students, I'll just repeat it. So, can I have the overhead camera, please? This is your image. I decide this is point C1. I decide this is the center of the image, right? So let this be the center of pentagon as well. This is one corner. Now, given these two conditions, can you find out the rest of the centers? And assuming it's a regular pentagon. Right? Because you know the angle this is supposed to make at the center and the angle between the two other centers. So assuming this is symmetric, you know this angle. You know this angle. This is equal to this angle, right? So you end up with these two. Similarly, you can find the other. Draw
4 minutes
the
remaining.
line. This is theta. This will be theta. This is theta. This will also be theta, right? So you can find the four corners like this. Can I have it back on the computer screen? For circle, you can use polar coordinates or you can use a warping function. Either is fine. Discuss your approach. Suppose if you want to do warping, then you can divide your squared image into 8 regions by vertical, horizontal, and the 2 diagonals. And you can use individual one to map to a pie with 45 degrees of angle between it, right? How many control points do we choose? As I mentioned before, there's not necessarily any minimum which you have to impose, but a general rule, more the merrier. So even if you have 6 variables, then you need 6 by 6 matrix, right? I would recommend by going with 6 by 9, 6 by 10, okay? Because it's non-linear mapping, so the mapping is linear, but the actual transformation is not necessarily linear. So no, the mapping is also non-linear. Anyway, yeah. So you have more control points. So you might want to use pseudo inverse instead of inverse. For 3A, you have the 9 filters. So basically, you have the texture raw, which is 1 to 12. You calculate the raw loss filters. These are the output images. Then you finally take you do this calculation for each pixel, right? Then you take the average of all of those. So when I take average of all the pixels in this, I'll get one number, right? So how many numbers will I get? 9. So my feature dimension would be 9. For each image, I'll get a 9 by 1 feature vector. So for all the 12 images, you will get 9 by 1 feature vectors, right? Then you use k-means with k equal to 4 to find out the clusters, right? That is what you're supposed to do. And the clusters which your algorithm finds should be consistent with what the actual true cluster should be. If you look at the textures, you would know which of them should belong to one type of texture. For problem 3A, yeah, this I already discussed. So for problem 3B, there's a difference in the approach. Now you don't have any more one number for each image directly, but you don't take the average of all the pixels. Instead, you use a window size. Now assume that your original image was, say, suppose for 256 by 256, right? So in the previous part, you took an average of entire image of 256 by 256, right? Now instead of doing that here, what you would do is you would take the average of a smaller region, say 15 by 15, 23 by 23. So for each pixel in the image, you take average of a window. Is that clear?
Out of time.
Try different values of W. Again, k-means. You can use, you can try several distance metrics. This is your original image. Suppose this is a dummy example. Then this is the result of the first iteration. And this is how your results are supposedly supposed to look like. Okay? And there are ways to improve the k-means algorithm. With the features, whatever number of features you have, you can also include the spatial constraint, assuming that at least 5 out of 6 textures are contained in a very closed region. One of the textures is spread out, and there's another texture in between. So for that, you can avoid using this feature, but otherwise, you can also add X and Y locations of the pixels in your feature vector. Does it make sense? We are out of time, so as it is, you've been given 2 sample midterms from the past, so that should be okay, I guess.
This concludes EE 569 discussion on Tuesday, October 22nd, 2013.
The time is 4 o'clock.